So with this thorough understanding of 2x2 systems, let's now move our attention to a general n by n system and discuss the stability of constant coefficient, linear constant coefficient, homogeneous, n by n systems of first order ODEs. And I'm not going to go through and classify all of the different types of equilibrium points we can have, because in general this is complicated, and you'll see this even if you go through and try and do what we just did for 2x2 systems, for 3x3 systems. However, we can get a basic idea of characterization for stability of systems of the form xi prime is equal to a xi, where xi at some initial condition t naught is equal to xi naught. And recall that we showed the solution of such systems is of the form xi of t for initial condition xi naught is equal to e to the a times t. This is the matrix exponential e to the at matrix multiplied by the initial condition xi naught. And we'll be considering this for systems where the determinant of matrix A is non-zero. So recall that the definition of stability means that the solution xi of t corresponding to an initial condition xi naught is stable on the interval from 0 to infinity, provided that for any positive epsilon, positive tolerance, there exists a positive delta such that if our initial condition xi naught is within delta of the origin, then the size of the solution xi of t corresponding to these initial conditions xi naught stays less than epsilon. Which means that e to the at times xi naught itself has to stay less than epsilon for t positive. We also have that xi of t is unstable if it is not stable in that it is globally asymptotically stable if it is stable and for any initial condition the limit as t goes to infinity of xi of t comma xi naught is equal to the zero vector. And this globally here just means that it happens for any initial condition, regardless of the initial condition. Or you can recall that because if the determinant of A is non-zero, the only equilibrium point will be the origin. So we'll really only have one equilibrium point, which can be either stable, unstable, or globally asymptotically stable. And using the condition that, or the solution in terms of a matrix exponential, it's relatively straightforward to go through and show the following theorem and how it relates to these stability conditions relate to the eigenvalues of the matrix A. So if A is a constant n by n matrix, we have that if A has an eigenvalue this means at least one, possibly more, with positive real part then the solution xi of t comma xi naught is unstable. Okay, this is something we definitely saw in 2D because with the whether it be a saddle point or an unstable node, asymptotically stable node, whenever we have a positive real part for an eigenvalue, the solution will shoot away from the origin eventually. For certain initial conditions. The next thing we can say is that if all of the eigenvalues of A with zero real part are simple, which means they have multiplicity 1, then the solution is stable. And this is also something that we noticed in 2D. This corresponds to the centers, where we have distinct complex eigenvalues but with the 0 real part. So the solution just oscillates around this equilibrium point, the origin, but never converges to the origin, so it's not asymptotically stable. And the last part of this theorem here is if the eigenvalues of the matrix A all have negative real part, or all of the eigenvalues, then the solution is globally asymptotically stable, or converges towards the origin. And a number of different these are proved in the book. I'm not going to go over the proofs in this lecture, but this is example 2.46 in the book if you're interested. This proof is not that out in the book, but they do go over how to kind of sketch it out and do it. It's based on the Putzer algorithm from before. And all of these are kind of related to this definition of stability up here in the matrix exponential and how that interacts with the norm. But the proof of 3 is in our book. Which is the book on advanced ordinary differential equations by Kelly. But just for example, we'll go over 2 separate examples right now to show how to apply this. If you look at xi prime is equal to x prime, y prime, z prime is equal to negative 2, 1, 0, negative 1, negative 2, 0, 0, 0, 1. So if we were to analyze the stability of this system, the determinant of the matrix A in this system is non-zero. So there's one equilibrium point, which is the origin. And the characteristic polynomial will be the determinant of A minus lambda I, which is going to be negative 2 minus lambda times the determinant of negative 2 minus lambda 0, 0, 1 minus lambda minus 1 times the determinant of the matrix negative 1, 0, 0, 1 minus lambda, which after a little bit of algebra simplifies to lambda squared plus 4 lambda plus 5 times lambda minus 1. And so the eigenvalues where lambda is equal to 1, and lambda 1 is the roots. Lambda 1, lambda 2 are the roots of this equation right here. So negative 2 plus I, lambda 2 is negative 2, or positive 2 plus I, and lambda 3 is equal to 1. Okay, you can see that by doing the quadratic formula here. The eigenvalues are where rho of lambda is 0. And this happens. And lambda is equal to negative 4 plus or minus the square root of 4 squared minus 4 times 5 times 4 times 1 times 5 over 2. Which results in negative 2 plus or minus the square root of negative 4 over 2, which is negative 2 plus or minus the square root of I. Oh, this should be negative 2 minus I, negative 2 plus I right here. Well, we have to conclude that the solution xi of t xi naught is unstable because the real part of lambda 3 is equal to 1, which is positive, greater than 0. This is very, very strong. This gives us the ability to tell, in a general sense, what's going on with the solution without even going through of a general n-by-n system without even going through and solving it. Now, you can still go through and you know how to solve this directly by finding the eigenvectors for lambda 1, lambda 2, and lambda 3, and then plugging into our formula from before, variation of constants formula using the fundamental solution. But it's really unnecessary if we're just going to talk about the stability of the actual the origin, or the one equilibrium point for the system. Oops, and I just realized I have a slight typo here. This shouldn't be the square root of I, this should just be I itself. Because the square root of negative 4 is 2 times I, divided by 2 is 1. This should just be I. Sorry about that. For a different example, right, consider the system that we talked about before, and we haven't written I think we've written down the system, but I'll just re-go over it. If we have, say, 2 linear springs, or 3 linear springs, connecting 2 masses, M1 and M2, we'll say the distance from equilibrium of spring 1 is u of t, and the distance from equilibrium for spring 2 is v of t. This is m1, k1, k2, m2, k3. From Newton's second law, we end up obtaining that for m1 u dot dot is equal to negative c u dot minus the force on m1 from spring 1 plus the force on m1 from spring 2, or the tension, sorry. So this is going to be due to the stretching of U and U alone. The tension due on mass 1 due to spring 2 is going to be V minus U. It's going to be due to the stretching, the difference between V and U, which is the total amount of stretching of spring 2. And Newton's second law for the second spring is going to be negative C V dot minus the tension on spring 2, or on mass 2, due to the difference V minus U, and then lastly minus the force due to the stretching V brought about by K3, the tension on M2 from K3, which is just due to V and V alone. We're also assuming a linear friction term. Of the form negative C times the velocity. So the spring tension is Ki times the stretching of the spring, and we have a linear friction term. Any of these can be changed if you want to complexify the model, make it more realistic. But if we make things more complicated, we're going to end up with a nonlinear system. So for the first equation, we have m1 u dot dot is equal to negative c u dot minus k1 times u plus k2 times v minus u and m2 v dot dot is equal to negative c v dot minus k2 times v minus u plus or minus k3 times v. Where we can now rewrite this by introducing a four-dimensional vector, xi1, xi2, xi3, xi4, where xi1 is just going to be equal to u, xi2 is equal to u dot, or xi1 dot, xi3 is equal to v, and xi4 is equal to xi3 dot, which is v dot. So So the system of 4 first-order differential equations that's equivalent to the system of 2 second-order differential equations will be the following system. Xi dot is equal to Xi2 and then Xi2 is equal to 1 over m1. Xi2 dot, I should say, is 1 over m1 negative c Xi2 minus k1 Xi1 plus k2 Xi3 minus Xi1, and then Xi4, and then 1 over m2 times negative c Xi4 minus k2 times Xi3 minus Xi1 minus k3 Xi3. Which is equivalent to the system Xi dot is equal to zero, 1, 0, 0, negative k1 plus k2 over m1 negative c over m1 positive k2 over m1 0, 0, 0, 0, 1 k2 over m2 0 negative k2 plus k3 over m2 and negative c over m2 times Xi1, Xi2, Xi3, Xi4, where this is the matrix A. This entire thing is A times Xi. So the solution of this system of 2 first-order ODEs is really equivalent to this system of 2 second-order ODEs, which constant coefficient linear is equivalent to the solution of this first-order homogeneous system of ODEs, which is very, very cool. And after relatively long calculation for the determinant of a 4x4 matrix, the characteristic polynomial can be shown to be lambda to the 4th plus c over m1 c over m2 times lambda cubed plus k1 plus k2 over m1 plus k2 plus k3 over m2 times lambda squared plus c over m1 m2 times k1 plus 2k2 plus k3 times lambda plus k1 times k2 plus k1 times k3 plus k2 times k3 all over m1 times m2. And I'm not going to go through and do, try to solve for the roots of this characteristic polynomial in general, because it'd be way too long. Even this calculation takes a little bit of time to get through. But the idea is that for maybe a specific example, we can go through and talk about what the stability of solutions to the system are going to be. So we'll take that very specific example. C equals K1 equals K2 equals K3 equals M1 equals M2. All of these values equal to 1. And when this happens, you get that row of lambda is lambda to the fourth plus 2 lambda cubed plus 5 lambda squared plus 4 lambda plus 3, which is lambda squared plus lambda plus 1 times lambda squared plus lambda plus 3. This polynomial factors to this quadratic or quartic polynomial factors to the multiplication of these two quadratics right here. And so the zeros of this characteristic polynomial is actually relatively easy to calculate. We can go through with the quadratic formula and get the two roots of this equation, lambda 1 and lambda 2, are given by negative 1/2 minus the square root of 3 over 2 times I, and lambda 2 is negative 1/2 plus the square root of 3 over 2 times I. And then, just like we can go through and get the two roots of this polynomial right here, we can go through and get lambda 3 and lambda 4. Lambda 3 will be negative 1/2 minus the square root of 11 over 2 times I, and lambda 4 will be negative 1/2 plus the square root of 11 over 2 times I. So we have 4 complex eigenvalues, each with the real part of the eigenvalue less than 0, and they're actually equal, they're negative 1/2, and therefore our solution will be asymptotically stable. Specifically, we'll say actually it's globally asymptotically stable. Due to the fact that each one of the eigenvalues is negative. And just like before as well, it's possible to go through and get the eigenvectors and the actual solution. If you want the actual solution, we call alpha 1 negative 1/2. We call beta 1 square root of 3 over 2, and we do the same thing for lambda 3 and lambda 4. We'll call alpha 2 negative 1/2 and beta 2 square root of 11 over 2. We'll put this to good use if you go through and calculate the eigenvectors. For lambda 1, the eigenvector becomes, that you end up solving for, will be 1 negative 1/2, 1, negative 1/2, minus I times 0 square root of 3 over 2, 0 root 3 over 2. And for lambda 2, we wind up getting the same expression, only with the positive. It's called the complex conjugate of this value. So we'll call this vector A1 and this vector A2. And likewise, you shouldn't be surprised that when you go through and do the eigenvectors for lambda 4, lambda 3, and lambda 4, you get something very, very, very similar. So similar, in fact, that I will just copy this over right here. The eigenvector corresponding to lambda 3, we'll call lambda 3, and this becomes square root of 11 over 2 here, square root of 11 over 2, but because alpha 1 is equal to alpha 2, this is the same. And then same thing for lambda 4, only with a positive value here. And so when you want to go through and get the actual real solution for this system right here, you have to go through and construct 4 real linearly independent solutions for your fundamental solutions matrix, and directly, in the exact same manner to how we did it before for 2x2 systems, you'll get that phi1 is A1 cosine of beta 1 times t minus b1 sine of beta 1 times t times e to the alpha 1t. Phi 2 ends up being a1 sine of beta 1 times t plus b1 cosine of beta 1 times t e to the alpha 1 times t. Phi 3 is a2 cosine of beta 2 times t minus b2 times sine of beta 2 times t e to the alpha 2 times t. And phi 4 is a2 sine of beta 2 times t plus b1 cosine of beta 2 times t times e to the alpha 2 times t. And the fundamental solutions matrix then is just the matrix composed with phi 1, phi 2, phi 3, and phi 4 as its columns. And the general solution to the problem will be phi of t times phi of t naught inverse xi naught. Where, by the way, this, for this problem, this is e to the a times t. This matrix is the same thing as the exponential matrix e to the at for these chosen values of k1, k2, k3, m1, m2, and c, which is very, very cool. But the main point here is that, right, without going through and doing the solution procedure, you can classify the stability of solutions. So this brings me to the last part of the lecture today, which is the concept of linearization of nonlinear systems. Of first order ODEs. This is a very useful concept that can allow us to use linear stability theory, the stability theory that we just developed for linear constant coefficient systems, on nonlinear systems. And it breaks down to, a good analogy for what it breaks down to is to think of approximation of a nonlinear function using the tangent line. So recall that in 1D, if you have a nonlinear function of x, say y equals g of x at any point, you can find the linearization or the tangent line approximation of that function. And in a very small interval around the point x naught that you're finding the linearization at, if the function is differentiable, the linearization is the best linear approximation of the function. So consider the following nonlinear system of ODEs. Xi prime is equal to g of xi with some initial condition. Xi of t naught is equal to xi naught. Remember that this is a system of n nonlinear first order differential equations. Xi1 prime is equal to g1 of xi1 through xn. This is an autonomous system as well. All the way through Xn prime is equal to Gn of Xi1 through Xn. With initial conditions, Xi1 of t naught is Xi1 naught, whatever that value is, all the way down to Xn of t naught is equal to Xn naught, whatever that initial condition is. Now suppose we wish to linearize system star around some point in n-dimensional space Xi star. This is, say, come up with the best linear system of ODEs that approximates around Xi star the exact solution. So if Xi star is a point, and we have some initial condition that's close enough to Xi star, Xi naught, or that in general the solution might orbit around like this. And if we get close enough to xi star, we want to find a linear system that approximates the solution to the actual solution. So if we zoom in close enough to xi star, you expect that the linearization will hopefully be a good approximation of the true solution. And this is directly possible to do. What we do is define the distance h, the distance vector h, which is xi minus xi star. Remember, this is the same thing as saying that xi is equal to xi star plus h, and h in general will depend on t, just like xi depends on t, but xi star is a fixed point. Well, if we differentiate this relationship, we get that h prime is equal to xi prime minus 0, because xi star is fixed, which is g of xi, which in terms of h is g of xi star plus h. And this is where we recall from multivariable calculus the multivariable Taylor series expansion. For each I from 1 to n, we have that hi prime is equal to gi of xi1 plus h1, xi2 plus h2, and so on and so forth, all the way up to xn plus hn. Which, as long as gi is a nice enough function, which, remember, we're assuming that g and its first derivatives are continuous, this will be equal to gi this should be xi1 star here. xi1 star, xi2 star, xin star. This will be equal to gi of xi star plus the first derivative of gi with respect to xi1 evaluated at xi star times h1 plus the first derivative of gi with respect to xi2 at xi star times h2. We go all the way up to the first derivative of gi at xin star with respect to xin and xi star times hn plus some error term of h, where the error term decreases to first order in h, or the limit as h goes to 0 of the the error term EI of H over the size of H has to be 0. So EI goes to 0 faster than the size of H. In our vector language, this is the same thing as saying that the derivative of the vector H is equal to the vector G of the point xi star plus the vector gradient of G1 at xi star dotted with H. But this happens for every I, so the second component over the gradient of G2 at xi star dot product with H, and so on and so forth for each one of the GIs all the way down to Gn dotted with H plus a vector error term depends on H, right? Epsilon of H is just all of the epsilon 1, epsilon 2, epsilon 3, all of the error terms for each one of the Taylor series expansions. Where you can say that the limit as H goes to 0 of the size of this error vector function over the size of H has to go to 0. This encapsulates all of these conditions. And so this is equivalent to H prime is equal to G of xi star plus the matrix of partial derivatives dg1 dxi1 dg2 dxi2 all the way to dg1 dxi2 all the way to gg1 dxin dg2 dxi2 xi1 d g2 dxi2 all the way over to dg2 dxin, and this goes all the way down to dgn dxi1 dgn dxi2 dgn dxin. So it's this matrix evaluated at xi star times H, then lastly plus the error vector epsilon of H. And so this is an exact equation. This matrix right here is called the Jacobian matrix of the nonlinear system, or the Jacobian matrix of G, the vector function G at the point xi star. we denote this as j of g evaluated at the point xi star. So a more compact way of writing the system is g h prime equals g of xi star plus the Jacobian matrix of g at xi star multiplied by h plus the error vector epsilon of h. And what's really cool here is that right, if h is small enough, right, what does this mean? Well, this means that the xi of t is close to xi star because xi of t is just xi star plus h of t. And that also means that the size of the error, E of h, is equal to the size of epsilon of xi minus xi star. If this is small enough, this error is approximately 0. It goes to 0 faster than h does. And so xi prime is approximately equal to, it's exactly equal to h prime, but if this is small enough, then this is going to be approximately equal to g of xi star plus the Jacobian matrix of g at xi star times h. And this is called the linearization of star. Specifically, this generates an inhomogeneous constant coefficient system called the linearization of star. So for fixed xi star, then the inhomogeneous linear constant coefficient system denoted by star L, which we'll say is eta prime is equal to g of xi star plus j of g of xi star times eta where eta naught is whatever h naught is, is called the linearization. Of star around or about the point xi star. And I want to make a note here. If xi star is an equilibrium point, of the nonlinear system star, then g of xi star is 0, the 0 vector, and the linearization star L is a homogeneous linear system. Which we know how to classify the critical points of. Because this thing, this vector, will be 0 at any critical point. So what we've just stumbled upon here is really quite incredible. And what it's saying is that at a given point in xi star, if we get close enough to xi star, we choose an initial condition that's close enough. Think of zooming in really close to xi star. The initial difference here is h naught, and the linearization is going to behave exactly the same as the actual solution if delta is small enough. Which means that even for a nonlinear system, if the determinant of the Jacobian matrix is non-zero, we can go through and use what we've done so far to classify the critical points of a nonlinear system, which is incredible. So I'll end by going over a couple different examples of this. The first is the damped nonlinear pendulum. Where xi is the angle and angular velocity of the pendulum. The system of differential equations is omega, or xi dot equals omega, and then negative r omega, negative g over L sine of theta. This is our vector function g of xi. The Jacobian matrix of this g of xi is going to be d g1 d theta, dg2 or dg1 d omega, dg2 d theta dg2 d omega, which is equal to 0, 1, negative g over L cosine of theta, then negative r, and furthermore recall that the equilibrium points of this pendulum problem are when omega is equal to 0 and theta is equal to 0 plus or minus 1 plus or minus 2 and so on and so forth. Or sorry, theta is equal to n times pi, where n is equal to these values. So on and so forth. So the linearization at an equilibrium point, at any one of these equilibrium points, g of xi star is equal to 0. This is going to, either any of these values for omega or theta is going to make this g right here equal to 0. And the linearization then will be around any one of the critical points. Will be eta prime is equal to matrix 0, 1, negative g over L cosine of n pi, then negative r times eta. With eta of t naught equal to whatever h naught is, where h naught is a vector that separates from this critical point. So we have a theta axis and an omega axis. Our equilibrium points look like this, and h naught will be a point that separates by a certain distance from one of these critical points. So cosine of n pi is going to be negative 1 to the n. If n is odd, it'll be negative 1, and if it's n is even, it'll be positive 1. And if this is our matrix A, you can go through and get the eigenvalues of A, or use what we did at the very beginning of the lecture, which is using the invariance, the trace of A is just going to be negative R, and Q, remember this is just the eigenvalues summed together for the sum of the diagonal points of the matrix, and Q is going to be the determinant of the matrix A, which is going to be 0 times negative R minus G over L times negative 1, which is just G over L times negative 1 to the n, for n any integer. And so we have that P is always less than 0, and Q is greater than 0 if n is even, we have that P is less than 0 and Q is less than 0 if n is odd. Which means that for odd values of n, we expect our solution to be asymptotically stable, and for even values of n, we expect there to be a saddle point. In the linearization, but because the linearization is a good approximation when we're around the actual system, when we're around the critical point, when we're very close to the critical point, this is enough to classify what we expect. And sure enough, if we do a plot of this system, this is exactly what we see. This is a plot of numerical solutions to the system in the phase plane, and we see very clearly that at the odd values, at the even values, this corresponds to n equals 1, n equals positive 2, n equals negative 2. We have asymptotically stable equilibrium points, and at the odd values of n, this corresponds to n equals negative 1, n equals positive 1, we have saddle points, which is a very, very neat method. So let's go through and really kind of practice this. We'll do this now for the non-dimensional Lotka-Volterra equations, which we talked about in class before. These are the predator-prey equations from our population models. So for these, you have the dimensionless prey population is x, the dimensionless predator population is y, and the system of differential equations ends up being the time derivative of xi is equal to a times x minus b times xy minus c times y plus d times xy. This is g of xi, where a, b, c, and d are all positive parameters that are found when non-dimensionalizing the predator-prey equations and represent the growth of the prey in absence of the predator, the rate of decrease in the prey due to the predator eating the prey, and same thing, this is the shrinking of the predator in absence of the prey, and this is the growth of the predator population due to consuming the prey population. The Jacobian matrix of this system is the matrix A minus by. It's the partial derivative of this with respect to x. The partial derivative of this with respect to y, which is negative bx. Partial derivative of this with respect to x is dy. And the partial derivative of this with respect to y is negative c plus d times x. Call that the equilibrium points of the system of differential equations star for this problem are the points 0, 0 and the points c over d comma a over b, or x equals 0, y equals 0, and x equals c over d, y equals a over b. And it should be clear that when you plug these two equilibrium points into the function g from before, you get that g of these points is equal to 0, 0 for either of these two equilibrium points. So the linearization then, we'll do 0, 0 first. At 0, 0, you get eta prime is equal to a 0, 0 negative c times eta, where the trace p is equal to a minus c, and the determinant q is equal to negative a times c, which is less than 0. So we expect that the 0, 0 point is a saddle point. And if we consider the other equilibrium point, which is the point c over d, a over b, you end up getting the linearization eta prime is equal to 0, negative bc over d, positive ad over b, 0, times eta, this is our A, and P is equal to 0 then, and Q is equal to this times this minus this times this, which simplifies just to positive AC, which is greater than 0, which classifies the critical point C over D, A over B, as a center, or more specifically a stable center, where around this point we expect the solution to oscillate but not converge. And sure enough, this is exactly what we saw. So if we open up a numerical plot of solutions in the phase plane, and this is actually a combination of some numerical plots along with the exact analytical solution, which we obtained. Right, we see exactly that the origin is a saddle point, and the other critical point right here is a stable center, but it's not asymptotically stable because the solution is not converging to that point. So this is really incredible. These two examples I think are good enough to emphasize the power of linearization for classification of critical points, but also for just getting the solution in a very small region, getting what the solution behaves like and what it looks like in a very small region localized around a point for a nonlinear system, which is very cool. But this is all that I wanted to talk about for this lecture. Thank you very much for tuning in. I hope you had a fantastic day.